Next we consider the multiplication instruction. Now, to multiplying two 8-bit numbers, so size of the maximum product is 16-bit, two 8-bit numbers multiplied it will give a 16-bit number. So, for example, this FF multiplied by FF, so it will produce FE01, which is 65025, 255 multiplied by 255. The instruction here that we have is MUL AB, and this whole instruction is the opcode, you see. So, though A, B they are specified separately, but they are we do not have any other operand that can be specified, and apparently it seems that there is a mistake between A and B, there should be a comma, but it is nothing like that. So, the whole instruction is MUL blank AB, and for multiplication this A and B registers should have the two numbers to be multiplied, and as a result this B register will have the higher order byte and this A register will get the lower order byte. For this particular multiplication example that we have, so this 01 it will go to A register and FE will come to the B register. So, there is no other way that by which you can do a multiplication in 8051. On the other hand, this division operation, so div AB, so here also we do not have any other way to specify other operands. So, it will divide A by B and A gets the quotient and B gets the remainder. So, that is fixed. Okay. And overflow OV bit is used to indicate a divide by 0 error condition. If there is an overflow, then division operation, then if this OV bit is set, so that will mean that there was a divide by 0 error, and this carry will always be set to 0. So, irrespective of the situation, so carry will be set to 0. So, that is the division operation. So, we have got multiplication division. If you remember 8085, we do not have any multiplication division operation in 8085, but in 8051 we have got multiplication and division, though only 8-bit in nature. So, if you want a higher sized multiplication, then you have to follow some multiplication algorithm by which you can multiply 8-bit numbers at a time. So, each 8-bit number can be considered as a digit, accordingly you can try to devise one multiplication and division algorithm. Another instruction that we are familiar with 8085 also, DAA, decimal adjust accumulator. So, here also we have that version, but in case of 8085 you remember that DAA, this whole thing was a single word. In this 8051 we have got DA as a word and A as another word, but again you cannot have any other operand excepting A. So, these operands are fixed. So, these operands being fixed, so you cannot modify it. So, what is required is that we should do the multiplication, we should do this addition, and then maybe we can do this adjustment. For example, in this case we are moving the number 23 hex to A register, 29 hex to B register, and assuming that we are treating them as decimal numbers. So, if it is a addition AB, so in case of hexadecimal the value is 4C hex. So, what in this particular example what we wanted is that we will do a decimal addition, that is 9 plus 3 12. So, 2 1 carry, then 2 plus 2 4 plus 1 5 52. So, the result that we expect is 52. But if you do a normal addition operation, then you will get add AB, where it will give us 4C hex. And as we know that for this conversion from this hexadecimal number to the corresponding BCD number, so we have to add 6 to the lower order nibble after the addition. So, 6 is added. So, with for this A equal to A plus 6, so the number from 4C it will become 52. Okay. So, that way we can do this decimal adjust instruction for converting into BCD number. Then we have got logic instructions AND, OR, XOR and NOT. So, these are the bitwise logic operations. Then we have got clear. So, we can clear a bit, and we can rotate a register. A register can be rotated via carry, without carry, etc. Then we have got swapping of nibbles. So, these logic instructions, they do not affect the flags in the PSW register. So, this is one of the very important thing to notice, that these logic instructions will not affect the PSW flags. Okay. So, we have to be careful while doing this check. So, ANL is AND logical. So, this will be doing bitwise ANDing. Then we have got ORL for OR logical, XRL for XORing operation, and CPL for complement. So, these are the examples by which these logical operations are done. Then address mode. So, we can have this ANL is AND instruction. So, you can specify A comma byte, where so one of the operand has to be the A register, the accumulator, and with the byte can be direct. So, you can have a direct 8-bit number, you can have registered indirect via say R0 R1, or you can have so you can have an immediate number, sorry, you can have an immediate number. So, hash, like you can say like say AND logical, you can say ANL A comma hash say 52 hex. So, A will be ANDed with 52 hex. Okay. So, that is the immediate mode, that is this immediate mode. So, you can have this direct mode, like you can say like AND logical A comma 52 hex. So, this means A will be ANDed with memory location 52. So, this means the memory location RAM location 52 hex. So, with that the ANDing will be done. So, that is the direct mode. Then we have got registered indirect. So, you can write in terms of @R0 @R1 like that. So, you can write like ANL A comma @R0. So, R0 and R1. So, you can say those two registers. Then we can have that is registered indirect, or you can have direct registered directly. So, you can say ANL A comma R0. So, R0 will be ANDed with AL with A register. So, this way we can have different AND logical instruction, or we can have byte A other way. So, this is the destination. So, direct byte and A. You can have byte constant, that also can be specified by hash constant. Then we can have this complement instruction like CPL A. So, the complement it will be complemented, the A register will be complemented, and we will get the value there. So, we can force individual bits to low without affecting other bits, like you can say like, so this is a single bit sort of thing. So, AND logical PSW hash 0x E7. So, the E7, this is the bit pattern 1110 0111. So, when you do ANDing with PSW, so PSW these two bits will be reset to 0, rest of the bits PSW register will continue to have its previous value. Or you can force individual bits high, like you can say OR. So, you can say ORL PSW 0x18. So, these two bits will be set to 1, whatever be the previous values of the bits in PSW register. So, these are useful when you are changing the register banks, okay, that we have 4 register bank select bits are there. So, without affecting other PSW bits. So, if you want to change this bank select, then you can use this OR instruction or say AND instruction. So, depending upon the bit pattern you want to set. Similarly, you can have complement bits by the XRL instruction. So, this will complement only this bit number 6 of the PSW of the P1 of the port P1. Other logical instruction we have got clear, we have got rotate left, then there is a rotate left through carry. So, this carry will also get affected. The RL instruction will not affect the carry, but RLC instruction will affect the carry. RR will rotate right, RRC will rotate right through carry, and swap, it will be accumulator nibbles will be swapped. So, this accepting swap other instructions we have seen in 8085 also. Those rotations are same as we have got in 8085, but swap, it will swap the two nibbles of the accumulator. Then clear. So, clear A will set all bits to 0, it will reset all bits of accumulator to 0. So, you can also say clear byte, where byte is specified in a direct mode. So, you can specify the byte. Then clear RI. So, this I can be 0 or 1. So, you can have it register modes, it can be 1 to 7, all those registers R0 to R7, all those registers can come. So, we can have this all these registers specified. Then clear RI. So, this is in the registered indirect mode. So, you can clear some memory location. So, this way we can clear the bits of some memory locations. This is the RLA instruction. So, as I was telling that it will rotate left. So, this MSB that we have will come to the least significant position, and these bits will get shifted by one position. Then we have got rotate right. So, rotate right will this is wrong, this should be RL, sorry, this is not RR, this is RL. So, then RR, so this is the rotate right. So, here this is rotated right. So, these bits will be going here and this bit will come to this LSB will come to the MSB position. So, that is rotate right. Then RRC, so it is rotate right through carry. So, this carry comes to the MSB position and this LSB position goes to carry and rest of the bits are shifted. Okay. So, and then similarly we can have RLC where this carry will come to the LSB, MSB will go to carry and rest of the bits will get shifted. So, these are examples by which you can do this thing. So, here also you get the set B instruction, that is for setting one particular bit. So, set B C will set the carry bit to 1. Okay. Shift and left is same as multiplying by 2 and shift by multiply and shift right is divide by 2. So, any number if you multiply it by 2, so it gets left shifted by one position, and if you are multiplying dividing by 2, so that is right shifting by one position. So, this is an example. First in the first instruction move a comma hash 3. So, we get the immediate number 3 in the accumulator, then we clear the carry and then we once we execute one RLC instruction rotate left through carry. So, what happens is that this carry comes to the least significant position and this 1 gets shifted to the next position. As a result, the number that we get is 6. You see, it is a multiplication by 2. If you do the step once more, then what will happen? So, another 0 gets shifted. So, this 1 gets shifted by one more position. So, you get the number 12. So, it is 6 multiplied by 2, 12. On the other hand, so these are actually multiplication by 2. On the other hand, if you do RRC, rotate right through carry, then the bits get shifted towards the right side and you get the number 12 divided by 2. So, get 6. So, this is useful. So, in many of the applications, so the multiplication and division, they are by powers of 2, and as a result instead of going for costly multiplication division operation, so we can go for this rotate type of instruction with much less number of clock cycles needed. This is particularly true for signal processing applications where we have got many such multiplication and division by 2 as the basic operand. So, this is the swap instruction. So, swap will swap the two nibbles, this higher order nibble and the lower order nibble. Like if you move a comma hash 72 hex. So, these 4 bits contain 7, these 4 bits contain 2. So, if you execute a swap instruction, so they will get exchanged. So, the content of A will become 27. So, they are shifted, they are swapped like this. There are some bit logic operations, bit level logic operation also, like you can specify individual bits instead of byte. So, you can specify individual bit also, like ANLC bit. So, it is AND logical carry with some bit. Similarly, OR logical carry with some bit, clear carry, clear bit, complement carry, complement bit. So, these are all bit level operations for logic, for bit level logic operations you can say. So, bit can be any of the bit addressable RAM locations or some location of the special function register or SFR. So, that way we can have these bit level operations done, and same as that byte level operation, here we can do bit level things. Next, we look into conditional jump instruction, unconditional jump instruction, then there are conditional jump instruction and call and return instructions. So, unconditional jump. So, we have seen that there is SJMP instruction for short jump. It is relative addressing with 8 bit 2's complement number. It can go to minus 127 plus 127 minus 128 to plus 127 location. Then we have got LJMP address, the 16 bit address, that is the long jump, and there is AJMP which is a 11 bit address. So, offset is 11 bit. So, this range is 2k, within 2k block of program memory you can jump. The jump at the rate a plus dptr. So, this is long indexed jump. So, dptr with that a value will be added and that value the processor will jump to that particular address. So, you can create some small infinite loops in this fashion. So, actually what happens is that many of the microcontroller applications, so they are embedded system application. So, embedded systems like say temperature monitoring system. So, it controls the temperature of a room. So, that program, it will continually sense the temperature values and accordingly control the heater or the cooler. Okay. So, that way that program never ends. Okay. So, that continually looks into the temperature values and does the control. So, that program does not end. So, if you look into that this type of programs, then you will see that at the end the program branches back to the to some infinite loop, and that way it continues. So, it is a typical example can be like this. So, move C comma P 3.7. So, this port 3.7 bit comes to the carry register, so the carry flag, and then the carry flag is moved to P 1.6. So, as a result, this port 3's bit number 7 is moved to port 1's bit number 6, and then SJMP starts. So, it actually continually copies the content of this bit onto this P 1.6. So, this way we can have infinite loop. So, SJMP type of instructions, so they can be helpful if this program is small enough, then we can have this SJMP type of instruction. Then this memory relocatable code. So, this is the memory specific not relocatable. So, some codes are like here. So, this code is memory specific, like this is LJMP start. So, it is 8000. So, next time the program is loaded from some other address. So, this LJMP start will not work correctly, as we have discussed previously. But see this when it is SJMP instruction on the other hand. So, this is relocatable in the sense that we have seen that while coding this instruction. So, we note down the distance from this point to the point where you want to jump. So, that value is kept as the part of the instruction. So, that value will be added to the program counter, and the system will jump to that address. So, this LJMP instruction, so they produce non-relocatable code, whereas this SJMP instruction they produce relocatable code. So, we can have also jump table. So, this DPTR jump table. So, say in the A register we have got this index number, then we rotate left A. So, rotate left A. So, that will be multiplying the index number by 2, and then we in the jump table we put all these cases, case 0, case 1, case 2, case 3. So, they are put here. Now, each of these instructions, so they will take 2 bytes. So, if this jump table address is say 9000. So, this at the rate A, so A value for the first one, this index number is say 5. Okay. So, 5 means that will be rotate left A. So, it is multiplied by 2. So, it is 10. So, as a result it will jump to DPTR plus 10. So, DPTR plus 10 will correspond to actually the case 5, because each of these AJMP instruction will take 2 bytes. So, that case 5 will be at byte number 10 starting from the offset jump table. So, we can have this type of jump tables implemented by means of this jump instruction. This jump at the rate DPTR instruction is useful when you are implementing this type of code lookup tables. Then we have got conditional jumps. So, these instructions will cause a jump to occur only if a condition is true, otherwise the program will continue, like say here move A comma P 1 and ZZ loop. So, this will continually be jump on 0. So, the 0 flag is set, then it will be coming to this loop instruction this point back, and then otherwise it will move the A register content to B register content. So, there is no 0 flag. Actually, if you look into this PSW register, so we do not have any explicit 0 flag. Okay. So, in case, so how does it check it? So, it checks the content of A register whether it is 0 or not at the time of executing this instruction. So, so that way it is in some sense it is good, because it does not depend on the some operation. Okay. So, whenever the accumulator content is 0, so if you execute a ZZ instruction, so it will find that the accumulator is 0. So, in this case it is documented also that way, that if A equal to 0, go to loop. So, we have never said that if the 0 flag is set, go to 0 or go to the loop point. But otherwise, so other flags, the carry etc. So, we have got some specific bit in the PSW register, but for 0 flag we do not have any such PSW bit. So, these are the various instructions of jump. So, ZZ relative address. So, jump, so they are all relative. So, one interesting thing that you note with the conditional jumps is that all these conditional jumps, they are relative jumps. So, their offset cannot be more than 256 minus 128 to plus 127. So, it always has to be in that range. Okay. So, this ZZ, JNZ, JC, JNC, so they are all different conditional jump instructions, and they are all relative jump instructions. So, what about if you need to jump beyond say 256 bytes? Okay. So, in that case you should have a small conditional jump followed by one unconditional jump. So, what I mean is that you can put a ZZ instruction like say ZZ L1, and that L1 you put another sorry, in this L1 you put say another jump instruction. So, if you have to make really a long jump, then you put one LJMP say L2, where L2 is far away in the program. So, L2 is somewhere here. So, what we do? So, by a small conditional jump we come to this point L1, and from that L1 we put a long jump and come to L2. So, this may be one way out, since we do not have this unconditional jumps, these conditional jumps to be long jumps. Okay. They are all relative jump and very these short jumps. Then there is a CJNE instruction. This is a very complex instruction in the sense that it compares the content of A register with the memory location. So, you can say like CJNE, you can say like CJNE A comma say 52 hex comma L1, something like this, where this content of A register will be compared with the memory location 52, and if they are not equal. So, A and 52 location, if they are not equal, then the system will jump to the relative address, otherwise it will not. So, this is a very complex instruction that way. So, but that is many times that is useful. In a single instruction we can compare and also jump. Okay. It is basically jump on 0 and this condition checking. So, both of them are taken together into a single instruction. Then we have this is a conditional, say this is one conditional jump example. Like in the high level, suppose we are writing like this: if A equal to 0 is true, then send a 0 to LED, that is LED will be turned off, and if we want to say otherwise we want to send 1 to LED, so LED will be turned on. So, what we do if so that A equal to 0. So, here I mean the accumulator register. So, it ZZ LED off. So, you jump on 0 to LED off. LED off will turn off the LED. So, it will clear this port P 1.6, assuming that the LED is connected to port 1's bit number 6. Okay. And then it will be SJMP to skip over. So, it will otherwise it will come to this it will come to this point. It will clear this. It will set B jump on 0 to LED off. So, if it is not 0, then it will turn on the LED. So, that is the second part, the else part is coded here. So, set B P 1.6. So, the LED is turned on, then it is SJMP skip over. So, it will come to this point. Otherwise it will be coming to this point, it will be clearing this P 1.6, and then this instruction is redundant. Maybe it is just reading the port 0 from A. It is reading port 0 into the A register, something like that, but that has this particular statement does not have any correspondence with this piece of code. Okay. This is just an example. More conditional jump instructions, we can have CJNE A data relative address. So, that we have seen. Then CJNE RN. So, we can compare this register with some data and then jump to relative address. Then we have got CJNE memory address like R0 and R1, they can be specified @RN data relative address. Then DJNJ decrement RN and jump on not 0. So, this is again another complex instruction, DJNJ decrement and jump on not 0. So, normally when we are executing some loop instructions, so you have seen that we decrement the loop counter, and if the loop counter is not 0, then we jump back to the start of the loop again. So, normally we have to use two instructions, one for decrementation and another for compare and then so jump. So, in that instead of that, so this DJNZ is a single instruction by which you can decrement the register value, and then if the register value does not become 0, so you can jump back to the relative address. And then we have got this DJNZ direct address and then relative address. So, the direct and this relative address. So, here also the same thing, it will decrement the memory location content, and then if the content is non-zero, then it will be jumping to the relative address. So, this is an iterative loop, like say for a equal to 0 to 4. So, we are executing something here. So, this loop, when it is converted into a program, machine like 8051 program, so it will look something like this. First, this a has to be set to 0. So, this clear a, then this loop body, the loop body is executed, then I value is incremented by 1, and we compare whether this a has become equal to 4 or not. So, if a is not equal to 4, then we go back to this loop. So, this way it mimics the behavior of this loop here. Of course, you can say that this particular check CJNE etc., so this should be done earlier, because otherwise normally this after this loop is initialized to 0, we do a condition check. But in this case it is not required, because assuming that a is not modified immediately. So, here a value is 0. So, there is no point doing this check at the beginning. So, this is fine. So, this will work fine for this particular code. On the other hand, if you have got a loop which goes in the descending way. So, for a equal to 4 down to 0, okay, descending loop. So, here we have to do it like this, say we take the register R0, initialize it to 4, and then we say DJNZ R0 loop. So, decrement jump on not 0 R0 to loop. So, we can do it like this. So, we have got iterative loops like this. Then we can have call and return instruction. So, call is similar to jump, but it will also push the PC value onto the stack before branching. So, we have got two versions, like just like this jump, we had got AJMP and LJMP. So, we have got A call and L call. So, A call, the offset is address is 11 bit wide. So, this PC address is 11 bit, and L call address is 16 bit wide. So, the PC address is 16 bit. So, so in the stack, in both the cases execution is same. So, in case of a call, this stack will be loaded with the next value of the program counter for returning, and then the program counter will get that at 11 bit address. And in case of L call, this again the same thing, this program counter will be saved, next program counter value for return will be saved into the stack, and program counter will be loaded with the 16 bit address.